Hello everyone. In this video, we will see about the classification of partial differential equations. Before going to see about the classification, first we see about the definition of partial differential equation. So, an equation which contains two or more independent variables is generally known as the partial differential equation. Suppose if we consider the equation 1, here x1, x2, etc. xn are independent variables, z is the dependent variable, and in that equation the dou z by dou x1, dou square z by dou xn square, etc. are denoted the partial derivatives with respect to the independent variables. Suppose if we have the equation like this form, means we can say that this is kind of second order partial differential equation. So next we see about the order of the partial differential equation. So order of the PDE refers to the highest order of the partial derivatives present in that equation. Suppose if we consider the first equation, here dou z by dou x and dou z by dou y are present. So first derivative occurred, so we can say that it is a first order equation. In the second equation, that is dou square z by dou y square equal to 1 plus dou z by dou y whole power 1 by 2. The highest derivative occurred in that equation is 2. So, this of order second. Similarly, we can speak about the degree of the partial derivative. That means we have to see the highest power of which the highest order partial derivative term is raised in that equation. Suppose if we consider this example, here the second derivative occurred but its degree is 1. So in the linear differential equation, dou z by dou x plus dou z by dou y equal to z plus xy, the coefficient of the dependent variable is constant. So we can say that this is a kind of linear equation. Suppose if we consider the equation like z into dou z by dou x plus dou z by dou y equal to z plus xy, then we can say that the coefficient of dou z by dou x is z, then it is a nonlinear term. So we can say that it is a nonlinear partial differential equation. Now we see about the applications of PDE. We know that PDEs are mathematical equations used to model a wide range of phenomena in engineering. PDEs describe the relationship between a function and its partial derivatives, and they are used to model many physical phenomena including fluid dynamics, heat transfer, and structural mechanics. Overall, it plays a significant role in modeling, simulation, and optimization of complex systems in engineering. The ability to describe complex physical phenomena using PDEs has significantly impacted the development of modern engineering systems, making them more efficient, reliable, and cost effective. So first we see about the second order equation in two independent variables. So consider the equation 1.1. Here we have Aij, that is also equal to Aji, that is it takes a symmetric form, and the coefficients of u's are the real valued functions in the space x1, x2, etc. xn. Now we can write the equation 1.1 in more convenient form as Auxx plus Buxy plus Cuyy plus Dux plus Euy plus Fu equal to G. Here the coefficients are functions of x and y and do not vanish simultaneously. Here we assume that the function u and the coefficients are twice continuously differentiable in the domain R square. Now we see about the classification of PDE, and it is related to the classification of quadratic equation of conic section in the analytical geometry. So consider just quadratic equation ax square plus bxy plus cy square plus dx plus ey plus f equal to 0, and it represents hyperbola, parabola, or ellipse. Accordingly, b square minus 4ac is positive, 0 or negative. So by using this, the classification of second order equation, it's based on the possibility of reducing the equation 1.2 by coordinate transformation to a canonical form at a point. Suppose if we consider a point x0, y0, then the equation is said to be hyperbolic, parabolic or elliptic according as b square minus 4ac is positive, 0 or negative at that point. If this is true for all points, then we can say that it is hyperbolic, parabolic or elliptic in a domain. In a case of two independent variables, a transformation can always be found to reduce the equation into a canonical form. So for that, we will use the new transformation, that is psi equal to psi of x comma y and eta equal to eta of x comma y. Now assume that here psi and eta are twice continuously differentiable and that the Jacobian determinant is not equal to 0 on that domain. Let x and y be continuously differentiable twice the functions of psi and eta. Then we have that the partial derivatives like this form that is represented here in equation 1.6. So substituting these values in the general PDE, we have the equation 1.7 with the coefficients a star, b star, c star and so on. The resultant equation is same as the equation like 1.4 and this is invariant under the transformation. So the Jacobian determinant b star square minus 4a star c star is equal to j square into b square minus 4ac and this is always not equal to 0. Also it should be noted that the equation can be of a different type at a different points of the domain, but for our purpose we shall assume that the equation under consideration in a single type in a given domain. Now we assume that the coefficients a, b and c alone, since the classification of equation 1.2 depends only on the coefficients on that coefficients. So we can rewrite the equation 1.2 as 1.10. So simultaneously the 1.7 equation becomes 1.11. So next we see about the canonical form. So we consider the problem of reducing an equation 1.10 to a canonical form. First we assume that a, b, c is 0. Let psi and eta be the new variables such that the coefficients a star and c star in equation 1.11 vanish. Thus from the equation 1.8 we have a star and c star value. Now by using these two values we can write the equation 2.7 and by using the equation 2.7 we have the equation 2.2. Along the curve zeta equal to constant we have d zeta equal to this one and so we have dy by dx equal to minus zeta x by zeta y. So we have the characteristic equations which are represented here, that is dy by dx equal to b plus or minus root of b square minus 4ac divided by 2a. And these equations are all known as characteristic equations of an ODE for family of curves in the xy plane along which psi and eta constant. The integrals of equation 2.6, that is the solutions of the equation 2.6 are called the characteristic curves. Since the equations are first order ODE, the solution may be written as pi equal to c1, pi 1 equal to c1 and pi 2 equal to c2, where c1 and c2 are all constants. Hence the transformation becomes psi equal to pi 1 of x comma y and eta equal to pi 2 of x comma y will transform the equation into a canonical form. So next we see about a particular case, that is hyperbolic type. here b square minus 4ac, the discriminant must be greater than 0. Then the integrals of equations, that is the characteristic equations, yield a two real and distinct families of characteristics, and so the original canonical equation reduced to u psi eta equal to h1, where h1 equal to h star by b star, and we know that always b star is not equal to 0 here. This form is called the first canonical form of the hyperbolic equation. Suppose if we consider new independent variables alpha and beta, and that is denoted by equation 2.8, then we have the equation 2.9, and that is called the second canonical form of the hyperbolic equation. Likewise, parabolic type, we have b square minus 4ac is particularly equal to 0. So, the equations, the characteristic equations coincide. Thus, there exists one real family of characteristics, and we obtain psi equal to constant or eta equal to constant. So, we have the equation of the form 2.10, and that is called the canonical form of parabolic equation. And that equation 1.11, that is our general canonical equation, can also be written as u psi psi equal to h3 star of psi eta u psi u eta. So if we choose eta equal to constant, then we will get that equation 2.11. If we choose psi equal to constant, then we will get the equation 2.10. Next we see about the elliptic type. Here b square minus 4ac is less than 0. So we have the quadratic equation 2.4 as no real solution, but it has two complex conjugate solutions which are continuous complex valued functions of the real variables x and y. Thus in this case there are no real characteristic curves. However, if the coefficients a, b and c are all analytic functions of x and y, then one can consider the equation 2.4 for complex x and y. So for that, we assume the Taylor series representation, and then finally we introduce the new variables alpha as 1 by 2 into psi plus eta and beta as 1 by 2 into psi minus eta. So that psi equal to alpha plus I beta and eta equal to alpha minus I beta. So first we transform the equations 1.10, then we have a star of u alpha alpha plus b star u b alpha beta plus c star u beta beta equal to h4. So we obtain this equation. With the use of this equation, we consider a star c star equal to 0. Then we finally obtain these two equations. Then these are satisfied only if a double star equal to c star and b star equal to 0. Hence the equation can be written in the form of a star star equal to u alpha alpha plus a star star into u beta beta equal to h4, or we can divide this by throughout by a double star. So we have u alpha alpha plus u beta beta equal to h5. This is called the canonical form of elliptic equation. So for example, we consider an equation y square into uxx minus x square into uyy equal to 0. If we compare this equation, given equation, with the general PDE, second order PDE, then we have a equal to y square, b equal to 0, that is the coefficient of uxy is 0, so b equal to 0, and c equal to minus x square, which is the coefficient of uyy. Thus b square minus 4ac is equal to 4x square into y square, which is always greater than 0, we know this, but when we have x and y values equal to 0, this is equal to 0. So this equation is greater than 0 except x and y not equal to 0. From the characteristic equation, we have dy by dx equal to xy by x by y and dy by dx equal to minus x by y. So we have these two equations, and which are represented by C1 and C2, and these are the curves in a family of hyperbola. So by using the transformation psi equal to 1 by 2 into y square minus 1 by 2 into x square and eta equal to 1 by 2 y square plus 1 by 2 x square, we have the equation that is partial derivatives related to this is uxx, ux, uyy, and we have finally the canonical form as u psi eta equal to eta divided by 2 psi square minus eta square into u psi minus psi divided by 2 into psi square minus eta square into u eta. So in this video we learn about the classification of a PDE and 3 types related to that. So in summary, if we take that the d square minus 4ec, the discriminant value, if it is greater than 0 then it is hyperbolic, equal to 0 then it is parabolic, and is less than 0 means it is elliptic type. So these are all the some of the references which I take for this lecture. Thank you all.